Alright, in this video is going to discuss finding those potential functions. So in the last video we ended with kind of being stuck, and we were in this goal of trying to determine how to figure out if f is conservative, and so that we can use path independence and make our lives a whole hell of a lot easier. And well, we got stuck by trying to find this potential function, okay? Because that would be the key to unlocking the fact that our vector field f would be conservative, okay? So again, we certainly need the criteria that f, vector field f, is the gradient of some potential function f. Okay, so here's the same example that we left off with last time, and I kind of provided a clue that, well, if we want this to be equal to, okay, and I'm just going to write want because we don't know, but we want this to be the gradient of f, right? Well, the gradient of f, assuming f is a function in x and y, okay, this would be equal to the gradient of f del x, or so del f del x, and then del f del y. Okay, so maybe if I set the components equal, it might provide some insight. So let's try del f del x is equal to 2xy cubed plus 1. Okay, well, this just means the partial derivative with respect to x. So if I find the antiderivative, okay, so integrate both sides with respect to x, what do I get? Well, I think I get f is equal to, let's see, this would be x squared y cubed plus x, right? Okay, but this isn't the whole story, right? There's normally a constant, right? But now, if we think about this multivariable function, right, this is function not just f, but I'm going to write f of x and y, okay? When I differentiate with respect to x, really this c is not a c, it's actually a function. It could be a function in g, okay? Or in a function in y, right? Because when I differentiate that, that would go to 0, it would be treated the same as a constant. So, so this part is kind of the next thing we need to investigate, okay? And to that end, I'm going to switch gears and say, well, if I set the first part, maybe I should look at the second part and then compare notes and see where we get, okay? So if I do just that, I look at del f del y. Okay, this is going to equal 3x squared y squared minus y squared, or y to the minus 2, I'm sorry. And then again, I'm going to find the antiderivative of each side with respect to y, and so I'm going to get f of x and y is equal to, okay, x cubed, or x squared, I'm sorry, x squared y cubed. Okay, so far those are matching. That's a good thing. Then after this, we will have, okay, integrating y to the minus 2 is y to the minus 1, and then divide by negative 1, so plus, and then I'm going to have a constant, okay? So now I need to just, again, take a moment and say, okay, well, I do have a constant, right? But again, if I have to work with a function here and then differentiate this with respect, this whole potential function with respect to y, this would actually be a function in x, right? Oh, okay, so now I need to compare notes. So what I can notice is that, and I'm going to write this in black just so it's all consistent, h of x. Okay, well, perhaps, and this is my conjecture, I could say that the overall potential function, okay, well, so again, my goal is to find this overall potential function, but I kind of want to assemble this almost in pieces, all right? So I'm thinking, all right, well, could it be the case that the x squared y cubed seem to be in common, so I'm going to say, well, it probably contains an x squared y cubed, okay? And then, well, I have an x and I have a function that is h of x. Could those be the same thing? Well, I don't know. Let's try it, maybe. Okay, so plus x. And similarly, I have this g of y, and there's, well, a thing that only has y over here. Let's undo that. Yeah, there's a thing that only has y over here, so could it be that the g of y is this? Well, I don't know. Let's try it out. Let's take this potential function, find, so we're going to check if we do f with, or the partial derivative of little f with respect to x, what do we get? Well, I think we get precisely 2xy cubed plus 1. Okay, that seems to match our vector field, and similarly f of y is equal to, let's see, it'll be 3x squared y squared, and then minus y to the minus 2. So this seems to work, and all we have to do to show conservative is show existence of a potential function. So there could be variations on this, so you could certainly have a plus constant at the end that is a true constant, and several variations, but we found one, it works. So we have this potential function that is, whose gradient is their vector field, so therefore the vector field is conservative, therefore the path is path independent, and therefore it makes our lives in computing a whole lot easier. Okay, so that I'm not going to go back and actually compute that example that we left off with in the previous video, but I'm going to leave you with all the tools that you will need to do it on your own.